Hello students. In the previous video, we finished nucleophilic substitution reactions, that is NSRs. That was category A. Now we start with second category of reactions, B part, that is elimination reactions. In this category, there is only one reaction in your syllabus, and that is dehydrohalogenation. In fact, this word dehydrohalogenation, it's a combination of two words. Dehydrogenation means removal of hydrogen. Dehalogenation means removal of halogen. So we can say that dehydrohalogenation means removal of HX, removal of hydrogen and halogen. See, when an alkyl halide which contains minimum one beta hydrogen atom. What is beta hydrogen? Hydrogen atom attached to beta carbon atom is beta hydrogen, and the beta carbon is the carbon next to alpha carbon. And if you remember, I told you alpha carbon is the one to which halogen atom is attached. So when an alkyl halide which contains minimum one beta hydrogen atom is heated with alcoholic caustic potash. Caustic potash is KOH, alcoholic solution of KOH, or alcoholic caustic soda. Caustic soda is NaOH. So we can use alcoholic KOH or alcoholic NaOH. Dehydrohalogenation reaction will take place. And this will lead to the formation of alkene due to the removal of halogen from alpha carbon atom and removal of hydrogen from the beta carbon atom. Since, since halogen is removed from beta carbon atom, this reaction is called a beta elimination reaction. For example, I'm labeled alpha and beta carbon atoms. There should be minimum one hydrogen at beta carbon atom. You know, this is CH3. So this is CH2CH. This is CH2X. When heated with alcoholic KOH, if it do not heat, even then the reaction will take place, but the reaction will be slightly slow, right? This will be elimination of H and X. Pi bond will be formed between these two carbon atoms. That is, product will be ethene. Halogen combines with potassium to give KX. H combines with OH to form water. The product obtained is an alkene and KX. Or I can say KX and water or NaX and water will always be one of the products formed. We take another example. This is 2-halopropane. As I've labeled, there are two beta carbon atoms. Hydrogen can be eliminated from either of these two beta carbon atoms. Now, if beta hydrogen goes from the right hand side, we get double bond on the right hand side. If hydrogen is eliminated from the left hand carbon, then we get a double bond on the left hand side. In this case, products are not different. It is same. It means doesn't make any difference whether hydrogen is eliminated from the left carbon or the right carbon. Does not make any difference. Only one product is formed, and byproducts will be same. No change in byproducts. Now, we'll take an example in which more than one different products are formed. There's no change in byproducts. If hydrogen goes from the right-hand carbon, double bond will be formed between carbon number 1 and 2. If hydrogen goes from the left-hand carbon, double bond will be formed between carbon number 2 and 3. It means two different products are possible. One is 1-butene, the other is 2-butene. Remember, both the products are formed, but one of them is major, the other is minor product. How do we decide major product? Major product is decided on the basis of Sayzeff's rule. Sayzeff, Sayzeff's rule. This rule is applicable in two reactions. One is this, and the other reaction is dehydration of alcohols, which in fact you have studied in 10th standard, you have studied in 11th standard, and that will be repeated in 12th standard as well. So what does this rule state? This rule says that during dehydrohalogenation of alkyl halides and dehydration of alcohols, major alkene formed is the one which is more symmetrical or more alkylated. You can see this alkene is more symmetrical because on both the sides there are equal number of carbon atoms. In this case, this is unsymmetrical because distribution of carbon atoms on both the sides is not equal or not close to equal even. Moreover, this alkene is more alkylated. Carbon atoms which have a double bond between them, they have two alkyl chains. Whereas in this case, there is only one alkyl chain attached to the left-hand carbon atom. So major product is this, not this. In the exam, you'll write only one product. You will not write both products. Only one. And which one? You'll write only the major product. I gave you two products just to explain how do we apply Sayzeff's rule, right? One more example. This is 2-halopentane. If hydrogen goes from the right-hand side, we get 1-pentene. If hydrogen goes from the left-hand carbon, we get 2-pentene. None of the two is a symmetrical alkene, but definitely second alkene, that is 2-pentene, is more symmetrical than 1-pentene. In this case, distribution of carbon atoms is 1 and 4. In this case, distribution of carbon atoms along double bond is 2 and 3. So this is more stable. This is the major product, not this. Right? Now, if there are two halogen atoms present in the molecule, we can use alcoholic KOH, but it's better to use a stronger dehydrohalogenating agent. That is, in place of alcoholic KOH, sodamide, which is a stronger reagent, that is preferred. I'll give an example. For this halogen, if hydrogen goes from the naturally one side, pi bond will be formed. Similarly, for the second halogen, when hydrogen is eliminated, we get one more pi bond. I can say this is double dehydrohalogenation. For that, double amount of reagent, that is 2 molecules of alcoholic KOH will be required. Byproducts will also be double. This will be 2KX and 2 water. See, in board exam, you can use 2 molecules of alcoholic KOH and we get the final product. But sometimes, be careful, sometimes in competitive exam, they they do not want alcoholic QH to be used for double dehydrohalogenation. In board exam, it's okay. So for competitive exam, they are looking for a stronger dehydrohalogenating agent, and that is NaNH2, that is sodamide. So in place of this, we use sodamide. We get alkyne. Byproducts will change. Byproducts will be two molecules of NaX and two molecules of ammonia. Right? So that you have to be careful. If you are answering a question in board exam or in any competitive exam, there may be a slight difference. The reactant is 1,2-dihalopropane. For this halogen, hydrogen will be removed from carbon number 2 only. That is this hydrogen. This will lead to the formation of a double bond. I'm writing in both the products. Double bond on the right hand side due to this dehydrohalogenation. Now, for this halogen, hydrogen can be eliminated from the right hand side or from the left hand side. If hydrogen goes from the right hand carbon, then we get one more pi bond, that is, we get an alkyne. But for this halogen, if hydrogen goes from the left hand carbon, then we get a double bond on the left hand side as well. It means there are two possible products. One is an alkyne, that is propyne. The other is a diene. Now, dienes are of three types. This you will not learn anywhere, nowhere there in your syllabus. One type of dienes are those in which two double bonds are separated from each other by more than one single bond. More than one single bond between two double bonds. They are called isolated dienes because double bonds are isolated. Second type is conjugated dienes, means alternate single and double bonds. And these conjugated dienes are the most stable ones. And third is this type, they are called cumulated dienes. In cumulated dienes, two double bonds are adjacent to each other. And these are the least stable. Why are they least stable? Because pi electron cloud, which are close to each other, they will repel, and due to this, energy will be high, stability will be low. Due to low stability, this is the minor product, and one alkyne, that is one propyne or propyne, is the major product. Byproducts will remain the same. There's no difference at all, right? No difference in byproducts. Similarly, if the reactant is 2,2-dihalopropane, 2,2-dihalopropane, in that case also, we can expect these two products. Major product will again be propyne, and second product will be the minor product. Now, coming to the reactivity order of alkyl halides in dehydrohalogenation. First reactivity order is iodoalkanes are more reactive than bromo, bromo more reactive than chloro, chloro more reactive than fluoro. The reason is bond length between carbon and halogen. More the bond length, weaker is the bond, and easier is to break it. Second reactivity order is tertiary alkyl halides in this reaction will react fastest, followed by secondary. Primary will react the slowest. Reason is stability of the intermediate carbonium ion. That is the reason. Now, you might think that when alkyl halide is reacted with aqueous KOH or aqueous NaOH, product is an alcohol, but in place of aqueous, if we use alcoholic KOH or alcoholic NaOH, product is not an alcohol, rather product is an alkene. This is a very important question asked in exam. Why it is so? See, aqueous KOH contains OH minus hydroxide ions, and hydroxide ions are weakly bases. They are weakly basic in nature, and due to this, they cannot remove H plus ion from beta carbon atom. On the other hand, alcoholic KOH contains alkoxide ion, RO minus ion. Alcoholic KOH contains alkoxide ion, and alkoxide ions are strongly basic in nature, due to which they can remove H plus ion from beta carbon atom. This is the reason with alcoholic KOH or alcoholic NaOH, product obtained is an alkene, whereas in aqueous NaOH, product obtained is an alcohol.